All right, so part two, we've got to talk about density, some unit conversions, significant figures. Again, all things that we've seen before. I probably, yeah, sorry. So probably most of this that we talked about already, you've seen before, maybe not the prefixes in this format with intro chem, but there is some familiarity there. So we're just kind of expanding on topics we learned in intro. Density is going to be something else. We've seen this before, right? Density is mass over volume. When we measure mass in chemistry, right, we're going to probably be using grams, kilograms, and volume is going to be milliliters or cubic centimeters, the cc. If you remember, a cubic centimeter and a milliliter are equivalent, 1 to 1. All right, and that's what I have for you down here. It's one of our 4 conversion factors I want you to remember, that a milliliter or a cubic centimeter are the same. So a physical property, right? We talked about that in the first part. This is something that we can use to help us classify matter. So I use the distinction or the example of distinguishing between copper metal and lead metal, right? Color is definitely one that would help us distinguish between the two, but we could use density as well. If we had equal volumes of both, the lead would appear much heavier because it's just got greater density. Density is an intensive property, which means that it doesn't matter if I have a kilogram of lead or a gram of lead, the density is the same. Intensive property just means it doesn't matter on how much of the sample I have. So the density will be constant. Now, if I change temperature or I change the state, then obviously density will change, but because we know molecules like to expand, right? All right, so let me open the chat. Sorry, I forgot to do that. I always forget something. Okay, so the question was about the tests and the final exam. Are you allowed to use a graphing calculator? So here's the thing. In my face-to-face lecture class, I do not allow graphing calculators because they have incredible storage memory spaces. And I have, over the years, had students that have taken the time to put a lot of information in those memory banks. More time than probably if they had just studied, but that's beside the point. So I typically don't allow graphing calculators. However, if you're using Respondus isn't going to be able to tell if you're using a graphing calculator or regular calculator. So there's really not much I can do about it. Anyway, that answers that question. So technically, yes, it's allowed. I prefer a scientific calculator, but I know that a lot of you have graphing calculators, you're used to it, you're familiar with it. I don't want you to stress on the test day with a new calculator. So if that's all you have, you can go ahead and use your graphing calculator. Okay, then back to where we were. So density. We are going to, in lab, not the first lab, which will be chemical physical properties, but the second lab, we're going to be looking at density. And we are going to determine the density of solids. We've got an aluminum bar and a glass sphere. And then we're also going to look at the density of a liquid. So if you are dealing with a solid, we know, again, density is mass divided by volume. So we have mass, pretty easy for a solid. We're just going to put it on the scale, get our mass measurement. The volume can come one of 2 ways. If it is a regularly shaped solid, meaning it's a prism, right, or something where we can measure length, width, and height. And again, my drawing skills are quite terrible. If I can measure length, width, and height, then I can find the volume that way. If it is an irregularly shaped solid, right, like some kind of I don't know, rock, for example, and it's not a perfect sphere or perfect shape, and we don't have a math formula for that, then what we can do is find the volume by the displacement of water. All right, and so that's the first example we've got here. It says a solid that has a mass of 25.22 grams is dropped into a graduated cylinder that has 15.6 milliliters of water, and milliliters is our unit of volume. The water level rises to 25.0 milliliters. And from that, we want to know the density of the solid. All right, so again, my drawing is probably not going to help you. My drawing skills are just not very good. But we're starting with 15.6 milliliters of water. That's the initial volume of just the water. Then what we'll do in lab is we'll put that metal object or glass sphere, whatever it is, into the graduated cylinder. And of course, the water level goes up, right? It rises to 25.0 milliliters in this case. And the way I always thought about it is the volume of water that moves out of the way must be the volume occupied by the solid. That made sense to me. So to find the volume of the solid, we want to take the difference in those two volume measurements, right? Because the volume of water displaced is the volume occupied by that solid piece. So we take the difference in those two volumes to get the volume of the solid, then mass of solid divided by volume solid, we get our density. So since we're going to be talking about significant figures anyway, we might as well go ahead and talk about it here. When you're doing this problem, you're doing the parentheses first, right? We're doing a subtraction. And the rule is when you add or subtract, you want to follow the decimal place rule, right? And it's always least wins. So the least number of decimal places. So both of these measurements that we have, 25.0, 15.6, they have one decimal place. So when we get the answer, we're going to keep that volume to one decimal place. So if you notice in those volume measurements, we lost a sig fig. We went from 3 and 3 to now only 2. But that's okay. When we do a difference, the question is, how far past the decimal were we able to measure? And the way these graduated cylinders are calibrated, they can only measure to one place past the decimal. So if I wrote my answer here as 9.40, the 0 is made up, right? Like there's nothing here that can measure to 2 decimal places. So I have to keep it to 1 decimal place. So that's why that volume of the solid turns out to be 9.4, not 9.40, but 9.4. So that's step 1, right? We do the subtraction, we looked at the decimal place. Now, the second part of this, when we go to do step 2, let me change the color of my pen. Now for step 2, because we're dividing, we're going to look at least sig figs, the number of significant figures. And our mass measurement on top has 4 significant figures. The volume only has 2, the 9.4, there's only 2 sig figs. So my answer can only have 2 significant figures. So that's why our answer here, if we compare it to what we were given in the original problem, you know, if you're reading this problem over, you're like, okay, 4 sig figs, 3 sig figs, 3. So least wins, right? We'll go with 3. It ends up being only 2 because when we did that difference, we got a volume of the solid, which is what we're using for the density determination, that only has 2 significant figures. And that's why the density can only go to 2 significant figures. So when you're looking at multiplying and dividing, you always look at sig figs. When you're looking at adding or subtracting, you just look at decimal places. But if you're doing both, then you have to round at each step appropriately to whatever rule applies. All right, so that's finding the density of a solid. If we have a liquid, typically what we do here is we start with an empty graduated cylinder and we measure the mass of it. And it's empty, so we know the mass of the container. Then we take that graduated cylinder and we put the liquid in it and we remeasure the mass. All right, and those graduated cylinders are supposed to look like they're the same. My drawing is terrible. Okay, so our original mass of the empty cylinder for this specific example, it says it is 156.23 grams. And when I put the water in it, or whatever the liquid is, unknown liquid, now the new mass of both combined is 169.72 grams, right? So that's from the scale, from the electronic scale. The volume is coming from reading that meniscus, which was, we'll practice this in lab. You probably remember it from intro, but that's from reading that meniscus. How much is in that container? What space is being occupied? That's the 15.0 milliliters, right? So there's our volume. So what we're going to have to do here is I have the volume of just the liquid. I need the mass of just the liquid. So I'm going to subtract these 2 mass measurements to figure out the mass of just the liquid inside the cylinder. So like we saw in the last example, since I'm doing the subtraction first, I'm going to follow the decimal place rule. So when I take 169.72 minus 156.23, 2 decimal places, I get 13.49, 2 decimal places. I lost a sig fig, but that's okay. I kept my 2 decimal places. So that's step one. And then step two, when I do the division of mass divided by volume, I'm going to look at sig figs. And I've got a 4 sig fig number divided by a 3 sig fig number. So my answer here is only going to have 3 significant figures. So density of this liquid, we found the mass of liquid added was 13.49 grams. The volume from reading that meniscus was 15.0 milliliters. So after dividing, I get a density of 0.899 grams per milliliter. All right, so as we were talking about with sig figs, the zeros are the only tricky digit. So like, for example, 15.0, why was that 3 sig figs and not 2? Whereas in the part 1 video, when we were looking at 1,350, we said that 0 is not significant. Okay, well, it's at the end, not significant. It's at the end and it is significant. So what's the difference? So the rules of significant figures is that number one, if it's not a 0, it's automatically significant. So the way I kind of think about it is a significant figure is a measured digit. Like whatever device you were using, you were able to write down whatever, 13.42, right? Those measured digits are significant. Now the zeros are tricky. Okay, there's 3 options for your zeros. Zeros, I'm going to make up a number, 0.02060. And I'll just put a unit on it because I'm a chemist and I think there has to be a unit. Okay, if it's not a 0, it's significant. So we know that that 2 and that 6 are clearly measured. They're sig figs. You can't change them. Change is the answer, right? If I put 0.0106, it's a different number. The zeros are the tricky digit. If they come between non-zeros, right, they are measured, right? It was 206, not 216 or 226. So that's definitely a sig fig. Now, zeros in the beginning that come before the first non-zero digit, these are called your leading zeros. They don't actually have to be there in the sense that we can get rid of them with scientific notation. So the zeros that come before the first non-zero digit are not significant. They are just placeholders. So it's not like I can just rewrite this as 0.206. It's still 0.0206, right? But I could, if I wanted to convert it to scientific notation, I could say, okay, well, it's 2.060 times 10 to the negative 2, right? So the zeros at the end, I'm going to put like a question mark on this because you have to ask yourself a question. The zeros that are after the last non-zero digit, they will only be significant if there is a decimal written in present anywhere in the value. So if I go back to that number we were looking at just a minute ago, that's the reason why that 0 was not significant, because there was no decimal here. And that means that's the way of saying that this is an estimate. It's about 1,350. It might be 1,349. It might be 1,351. Not really sure, but it's about 1,350. So that 0 is just a magnitude 0. We just need it for size, but it's not measured. If it's at the end of the value after the last non-zero digit and there's a decimal present, then we measured that. The device we used actually helped us measure that. So this one is significant because there is a decimal present. All right, if it doesn't have a decimal, then it becomes a little bit different. We'll do some examples here. So 105, 3 sig figs, 0 in the middle, always significant. 0.0067. The way that, and I have to say as a student, this tripped me up the first time. The way that I think about this is if I go into lab and I have an electronic scale and I put something on the electronic scale and it gives me 0.0067. The zeros in front, there's nothing yet there to measure. It's just 0. There's nothing being measured there. The 6 is the first measurable amount. So when you're writing a number, the very first significant figure is the first non-zero digit. Anything before that, just as a 0, is just a placeholder. That's it. It's just there for size. Now, zeros at the end, they are significant if the decimal's written in. So 20.0, Those two zeros are in their same rule. They're at the end of the value, meaning they're after the last non-zero digit, and there's a decimal present. So all three of those digits are significant. But if I write 250, just no dot, that again, that's kind of saying about 250. Now, different books like to handle this a little bit differently. Some textbooks will say, okay, if you write 100, right, and you just leave it like that, you're telling me that the only significant digit you have is the 1, right? So because you're not putting the decimal on, you're saying that this is only good for one significant figure. If you write 100 and you put the decimal on, that's telling me that there are 3 significant figures. Now, other textbooks will say, I don't like that. That's really ambiguous. So instead, let's be perfectly clear and use scientific notation. A lot of students don't like scientific notation, but I will say that's the benefit of it, is that it takes out all the confusion with sig figs. If I have 100 and I want it to only have one sig fig, I'm going to write it as 1 times 10 to the 2, right? There's my significant figure. There's my magnitude. There's my significant figure. There's my magnitude. However, if I have 100 and I want it to have 3 sig figs, then I'm going to write it as 1.00 times 10 to the 2. There's clearly my 3 significant figures. And if I get into a sticky spot and I need 100 to have 2 significant figures, then the decimal, that's not going to help or hurt me, because if I leave it off, it's only 1 sig fig. If I put it on, I got 3 sig figs. So this is one of those cases where I have to use scientific notation in order to do this right. And in that case, I would do 1.0 times 10 to the 2. So sometimes, not often, but sometimes it'll happen where really the only way to be clear with sig figs is you have to use scientific notation. But I will say that is the benefit of scientific notation, is that it makes the number of sig figs very clear. The exponent is just the power. Whatever's in front is automatically a sig fig. So 1 sig fig, 3 sig figs, 2 sig figs, it takes all the guessing game out of it. So a lot of books, including Tro, the one that we have now, they want you to use this, the scientific notation, because they say that, this decimal thing is a little ambiguous. So 250, if I want it to be clear that it's only 2 significant figures, it would be 2.5 times 10 to the 2. All right. I don't mind the decimal rule. I think it works fine. Now, something we've already discussed is that if you're doing calculations that are just addition or subtraction, that's all we're doing. What we want to focus then on is how far past the decimal place do I know for sure? The idea behind this is if I go into lab and let's say I use a triple beam balance to measure the mass of object A, whatever that is. Let's say it's a beaker, and I get 15.22 grams. And then I use an electronic scale, a milligram balance, to measure object B. And the milligram balances can go an extra decimal place. All right, and I get 10.016 grams. If I ask you to add those two together, right, what is the sum of the mass of object A and object B? The idea is that in the first measurement, the 15.22 on the triple beam, it's not calibrated to give me that third decimal place. So what that means is that I don't know what that number is, because that device can't do that. It just isn't calibrated to do that, which means I can't say for sure that the 6 is going to stay a 6. So what you do is you follow your least decimal places. Object A, 2 decimal places. Object B, 3 decimal places. So my answer for the sum can only have 2. Right? Least always wins. So 2 decimal places. So when I add this all up, I get 6, 3, 2, and then 5 and 2. And what I would do here is I would cut, right? I would have to cut off that 6 in the third decimal place, because again, I don't know what it's being added to, so I can't say for sure it'll stay 6. Rules of rounding, whatever I'm cutting off, if it's 5 or greater, it's going to make the previous digit go up by 1. So this is going to become 25.24 grams for the sum of those two masses. All right. Now that rule, sometimes students, it's kind of easy to forget because it's not often that we only do addition and subtraction. Normally we're doing multiplying and dividing. If we're doing multiplying and dividing, then much easier. This rule students don't forget, you follow the least number of sig figs, right? So that one's easier. Like we saw with density, if you have to do both types of operations, then you have to round at each step, following the appropriate rule for whatever operation you were doing. So let's do some practice. So what I did for these is I gave the problem, I gave the answer, and then we're going to talk about where we round it to. So I got 48.2 added to 3.82, added to 48.4394. Type it in the calculator, 100.4594. Since all we're doing is adding, we're going to look at the decimal place rule, right? So whenever, if we're just adding or subtracting, all right, we're going to follow the DP, decimal place rule, all right? So least always wins. So if I look at my first measurement, 4 places past the decimal. Another measurement, 2 places past the decimal. The 48.2, only 1 place past the decimal. This is going to limit how far I can go. That one's the least. So my answer here, that's where I have to limit it to. It's not how many sig figs, it's the decimal place. Now, what I'm cutting off though, the 5 or greater, means that previous digit, the 4, has to round up. So I'm going to leave that as 100.5. All right, notice it's not sig figs, right? 3 sig figs became 4. It's not sig figs we're looking at. It's the decimal place, right? How far past the decimal should we go? Next example. All right, again, all we're doing is addition. So again, we're going to look at the decimal place rule. So first measurement doesn't have any decimal places. It just goes to the ones place. Second measurement, 2 places past. Third measurement, 4 places past. So least wins, right? So we have to stop right at the ones place. So I have to be a little bit careful here, because if I just put 150 and I don't put the decimal on, that's saying that the 5 is it's the last sig fig. Because I need that 0 to be a significant figure, right? Because we're going all the way to the ones place. I want to make sure and capture that with the decimal, all right? Next one, all we're doing is addition and subtraction. So again, same thing, decimal place rule. 3 decimal places with 1 decimal place, 2 decimal place with 3, least wins. So the 5.3 with only 1 decimal place is going to limit how far we can go for the answer. So the 6.319 answer is going to round to 6.3. All right, just to that 1 decimal place. All right. So for each of those practice problems, A, B, and C, all we were doing was adding or subtracting. So that's when you follow decimal places. How far past the decimal, least always wins. When I get to part D and E, we're going to start mixing. Now, do parentheses first. So 51.5 added to 2.67. I'm going to round that to 1 decimal place because of the 51.5. The 33.42 minus 0.124, I'm going to round that to 33.30, 2 decimal places because of that 33.42. Now I've got 2 numbers that when I multiply them together, I now think about sig figs. 54.2 has 3 sig figs. 33.30 has 4 sig figs, least wins. So we're going to go with 3 significant figures. And as I mentioned, there are occasions, not often, but there are occasions when you have to use scientific notation in order to get the right number of sig figs. So 1804, right? If I had rounded that to 1805, that would have been 4 sig figs, right? And we want 3 sig figs. If I had rounded that to 1800, that would have been only 2 sig figs. So the only way around this is to do scientific notation. 1.80 and then times 10 to the 1 to positive 3. All right, so let's do 2 more examples here. So I'm going to grab my calculator. First parentheses, I have 125.1 minus 1.22. So calculator gives me 123.88. But I'm thinking here, I want to look for just one decimal place. So I'm going to take that 8 in the first decimal place, but I'm going to round it up because what I'm cutting off is 5 or greater. So this is going to become 123.9. All right. So that's that first one. Then I'm going to divide that by, over here, I'm going to take 52.5 added to 0.63. So 53.13, but again, one decimal place is as far as I can go. So that's going to get rounded to 53.1 milliliters. All right, now I'm going to look at significant figures. So I'm going to take 123.9 divided by 53.1. And when I get my answer here, my mass has 4 significant figures. My volume has 3 significant figures. So my answer should only have 3. So we're going to go 2.33 and stop there. 2.33 grams per milliliter. Okay, units didn't cancel out because it's a density, right? All right, then the next one, I'm going to take 47.5 minus 1.44. So I get 46.06, but only going one decimal place. I'm going to go 46.1 kilogram. And then I'm going to divide. Now, what I have here are 3 things being multiplied together. So you have an option. Option 1 is you multiply these 3 things together, round to 2 sig figs, figure out what that volume is, and then do the final division. However, that's not the better way to do it. The better way to do it is option 2. Because at this point, we took care of the decimal place rule, everything from here on out is either multiplying or dividing. So really what I'm going to do is I'm going to take 46.1 and I'm going to divide by 10.5 times 0.35 times 0.175 in parentheses and enter. That'll be more accurate. So this right here, I just plug all of this into the calculator. And if you noticed, when I hit the end of that parentheses, it was a very exact number. Rather than rounding that to 2 sig figs, it kept all those digits. And then dividing that 46.1 by that answer, now I can look at how many sig figs should I have? 3 sig figs, 3 sig figs, 2 sig figs, 3. We're going to go with the least, which is 2. 71.68 would round to 72. All right, and then our units would be kilogram per meter cubed, because meter times meter times meter is a cubic meter. And that's another density unit, just looks a little bit different. Okay, so again, on the calculator, once we did the subtraction step and we got the correct number of decimal places, then what I did is I hit divide and I went ahead and used the parentheses. 10.5 times 0.35 times 0.175 end parentheses. See, so instead of rounding that to 0.64, all the digits are kept. Then I hit enter and then I get my answer and I round it to least sig figs. And that is the 0.35 is 2 sig figs. That's my least. So that's why my answer here would only have 2 sig figs. Okay. All right, then next page. All right, precision versus accuracy. All right, so what's going to happen here, and I use lab as kind of an example. A lot of times now in lab, there's going to be 2 trials. We're going to do the experiment and then we're going to do it again. The reason for that is I can look at your precision. Precision is like repeatability. So if you're able to repeat your results time and time again, that means you have very good precision. Accuracy is that you actually get the right answer. And they're not necessarily the same. You can have students that have what appears to be good accuracy and poor precision. And then you have students that have really good precision, but bad accuracy. So what you are given in terms of the definition, precision is the range of answers. If the range is very narrow, you have very good precision. If your answers are all over the place and you have a big range, then that means your precision is not so great. Accuracy is how well your average matches the actual value. All right. So if we're finding aluminum, density is 2.7. We know that that's the actual density of aluminum. Group A does 3 density determinations, and they get 2.63, 2.62, 2.63. Precision looks phenomenal, right? Then group B, 2.55, 2.85, 2.7. Not terrible, but definitely not as good as group A in terms of precision. But their average is right on the money. Whereas with group A, the average wasn't quite as good. So when you look at this, group A has a very small range of answers. So group A has much better precision. They were able to get the same answer pretty much over and over again. But group B, because the average matches the known value, they're the ones that actually had better accuracy. All right. And that may seem strange, but we look at both of those now in Chem 1. All right. All right. Now, dimensional analysis. This is where we're going to start doing our unit conversions. Then we're going to be using this a lot when we get into stoichiometry. So as I had mentioned in the part 1 video, we are going to be doing unit conversions to get us right on the SI system. Sorry if I move that too quickly. There are 4 conversion factors that I want you to memorize. I've highlighted those here. There's one for length, which is 1 inch is 2.54 centimeters. There's one for mass, which is the kilogram is equal to 2.205 pounds. For volume, there's the cubic centimeter and the milliliter. Those are 1 to 1. And there's also one more for volume I want you to remember. And that is a gallon is 3.785 liters. Those are the 4 I want you to remember, all right, for the first test. Any other unit conversion I'll give you, but those are the ones I want you to remember. All right, so how do we do dimensional analysis? When we're doing unit conversions, we start with the given measurement and we set up our conversion factor such that units in the numerator and the denominator cancel out. It's like x divided by x. So it goes away. And then the unit you're looking for goes on top. And what you put into this conversion factor is called an equivalent statement. So what we learned with the prefixes in the part 1 video is that a millimeter, right, milli, is equal to 10 to the negative 3 meters, right? Now you don't have to put the 1 in front because it's just a 1. So that's why 10 to the negative 3 meters is equal to 1 millimeter. The equal sign is this line right here. It's an equivalence line. So what you put above and below have to be equal to each other to be a conversion factor. And then your units cancel out, top and bottom. So that's how they work, nice and logical. So the next one, we have 0.556 kilometers, and we want to convert that to feet. And you might look at this first and be like, okay, I think I know how to do this, but this is going to take a while. And you might be able to Google very quickly the conversion from kilometers to feet. We're going to do this the long way to help us get used to it. So first thing I'm thinking is kilometer can go to meter pretty easily because that's just a prefix. Meter can go to centimeter pretty easily because, again, that's just a prefix. I now learn and highlighted, right? I'm going to remember how to go centimeters to inches. And then to finish it, I gave you the conversion of inches to feet because most of us know that, but on test day, it's real easy to forget, right? So 12 inches in a foot. So first conversion step, right? We're going to put kilometer in the bottom, meter on top. This is just the prefix that we saw in the part 1 video. So when you have a prefix conversion, you put 1 wherever the prefix is, and then substitute that prefix on the other side with the exponent. So kilo is 10 to the positive third, all right? Next conversion, we're going to get rid of meters on the bottom and go to centimeters. Now, if you were an intro, you'd put 100 centimeters on top, 1 meter on the bottom, you'd be good. If you want to keep doing it that way, do it that way. The TRO way, the Chem 1 way, is wherever your prefix is, you put the 1, and then on the other side, the prefix is replaced with the proper exponent. So centi is 10 to the negative 2. All right. So canceling out our units as we go. Kilometers canceled out. Now we've got meters canceling out. Now we're going to get another conversion here to go centimeters to inches. 1 inch is 2.54 centimeters, right? Here's my equivalent statement. 1.00, I'm just going to write it as a 1, but just don't limit your sig figs by it. 1 inch, right, is equal to, this is my equal sign, the equivalence line. And then on the bottom, 2.54 centimeters. And I knew to set it up this way because I knew I wanted centimeters to cancel out. So that's why I did it that way. All right, last one. We're going to need inches on the bottom, and then we can put feet on top. So 12 inches, right, is equal to 1 foot. All right, and now we've canceled out inches. We've gone to feet. So on the calculator, I'm going to take 0.556. and I'm going to multiply it by 10 to the third. All right. Then I'm going to divide it by 10 to the negative second. Then I'm going to divide that by 2.54. And then I'm going to divide that by 12. Anything on the top, multiply. Anything on the bottom, you divide. Calculator gives me 1824.147 feet. And of course, before we're done, we have to go back and think about sig figs. Now, with significant figures, the conversions are exact values. We don't want to limit the sig figs by the conversions. We want to go to the measurement, right? What was the measured digit? The idea is when we do calculations with our measurements, the answers shouldn't be more or less precise than the measurements that we took. If we go into lab and we have really great equipment, we can take really precise measurements, we can get really precise answers. But if we don't have great equipment and we can't really take very precise measurements, then our answers can't be that precise. That's the idea. So our measurement in the beginning, 0.556, had 3 significant figures. So my answer should only have 3 significant figures. So I'm going to take the 1, 8, and the 2, but I can't just round it to 182 because now I've lost magnitude. I'm in the hundreds rather than the thousands. So the 4 that we're cutting off, because we're not quite to the decimal yet, we're going to replace that with a 0. And then we're going to add feet. Now, if you want to follow the Tro way, you're going to say, really, the better way to do this is scientific notation. And we're going to say 1.82 times 10 to the third feet. Or if you want to do 1.82 kilofeet, which sounds weird, but it would be accurate. All right. So that's how we do our dimensional analysis. If we have a area unit, Tro way, sorry. Tro is just referring to the textbook. So the 1824, when I look at this and I want 3 sig figs, the decimal with the 0 at the end, that rule works, right? If I leave the decimal off, I'm saying that that 0 is not a sig fig. It's just for size. So I clearly know this is only 3 sig figs. Tro, along with other textbook authors, will say, that's really ambiguous. Let's be very clear and put it into scientific notation. So I accept either one because I think they're both perfectly fine. But that's what I meant by the Tro way. Sorry about that. That means be picky and put it into scientific notation. All right. Now, if we have an area unit, something that's squared, or if we have a volume unit, like something that's cubed, if we're going to do a unit conversion for area or volume, we have to be careful with that dimension. In other words, this is a 2-dimensional unit. So if I take 2.54 centimeters equal to an inch, I have to do that twice. Because if you think about it, an area would come from taking, height times or length times height, right? So you'd have to know your length measurement and your height. You'd multiply the 2 to get your area. If I don't have each individual measurement, I can't convert separately from centimeters to inches, but I would still have to do that conversion twice. And that's what this is showing you, that if your unit is squared, you have to square the conversion factor. All right, so we're going to try one of those on the next page. So I've got 1.56 times 10 to the fourth cubic inches. And I want to convert that to cubic meters. So first, let's kind of collect our thoughts with the unit conversions. What we know is 1 inch is equal to 2.54 centimeters, right? So we know that. Then centi is just a prefix. So we also know that a centimeter is 10 to the negative 2 meters. Now, those conversion factors are just for one dimension. That's just for the length. It doesn't do all length, width, and height. I'd have to do it all 3 times, right? Because this is a volume unit, length times width times height, we got cubic inches, but we need it in cubic meters. Now, you don't really have to stress about it too much. Your power on the unit will tell you exactly how many times you got to do those conversions. So what I'm going to have to do to both of these conversions is I'm going to have to cube them, because that's what that unit tells me to do. It says you got to cube it. All right. So what I'm going to do is I'm going to rewrite these. I'm going to cube everything in that parentheses. So 1 times 1 times 1 stays 1. Inches cubed, just cube the unit. On my calculator, I'm going to take 2.54 and I'm going to cube it. So not times 3, but cubed. So in other words, 2.54 times 2.54 times 2.54. Now, if you want to keep 3 sig figs and round this to 16.4, go for it. I usually keep 16.387 just because, but if you only do 16.4, it's totally fine. All right, so just to show you again how I did that, I got 2.54. There's my y to the x, so raised to the third power, enter. So there's my 16.387. So 2.54 cubed, 16.387, and then centimeters cubed. All right, then the next conversion, 1 cubed stays 1, centimeters cube, so 1 cubic centimeter, is equal to 10 to the negative 2 raised to the third power, means you multiply your exponents. So that's 10 to the negative 6, and then meters cubed. Okay, so we cubed everything inside the parentheses for both of those conversion factors. Now I'm ready. So I have 1.56 times 10 to the fourth inches cubed. First conversion step, I want inches cubed on the bottom to go away. Looking at my equivalent statement, 1 cubic inch. Okay, so just kind of showing you, I'm taking this conversion and putting it here. Okay, 1 cubic inch is equal to 16.387 centimeters cubed. All right. Then for the next conversion step, using my purple pen, all right, I'm going to take centimeters cubed on the bottom, 1 cubic centimeter, so that they cancel out, is equal to 1 times 10 to the negative 6 meters, or 10 to the negative 6 meters. All right, so on my calculator, all right, I'm going to use the exponent key. Okay, so what's going to happen on my calculator? I'm going to take 1.56 times 10 means EE. See how the little exponent popped up? And then I'm going to put in the 4. So there's my 1.56 times 10 to the 4. So let me show you that one more time. 1.56 EE4. Then I'm going to multiply 16.387. Okay, and then I'm going to multiply that by 1 EE negative 6. Enter. And there's my answer. Starting measurement, I have 3 significant figures. So my final answer can only be 3 significant figures. So I'm going to take 0.25, the second 5, because I'm cutting off that 6. I'm going to make that second 5 round up to a 6. So this is going to become 0.256 for my final answer. So 0.256 meters cubed. Okay. All right. And then there's one more here, which is slightly more complicated because it's got 2 units. So I just want to show you how this will work. When you see this problem or this measurement, it says 14.70 pounds per square inch. All right. So just to show you, that slash right between pounds and squared inches is the same as that line right there that I highlighted. It's an equivalence line, right? And what I need to do is have this convert to kilograms per meter squared. So the reason why this is more complicated is I've got to convert my unit of mass from pounds to kilograms, and then I have to convert my unit of area from squared inches to squared meters. Let me do the mass part first. Okay, so in my conversion, I'm going to get rid of pounds and I'm going to go to kilograms. So the conversion here, a lot of students remember it. It is one of your 4 to memorize. They just put the 2.205 in the wrong place. So 1 kilogram is 2.205 pounds. When I was learning this, I did kind of confuse myself because I was thinking about weights at the gym, and anyway, the way I made it stick, because then it was like, okay, I got it. Pounds is the bigger number. All right, that made it easy. So wherever pounds goes is where the 2.2 goes. The 1 goes with kilograms. So pounds is always the bigger number. So 1 kilogram is 2.205 pounds. All right, so we got rid of pounds, we went to kilograms. Now, when I took care of the mass measurement, the unit. Now what I'm going to do is I'm going to pretend like that's not there. And now I'm going to look at my area unit. So when I go to my next conversion step, the inches squared is going to have to cancel out in the numerator. All right. And then like we saw in the last example, we're going to go to centimeters first, but it has to be squared centimeters. And then in the next conversion, we're going to get rid of centimeter squared on top and go to meter squared on the bottom. All right. So we had to do that first conversion was for the mass unit, getting rid of pounds, going to kilograms. Now we're going to cover that and deal with the area. Inches squared, top and bottom, cancel, go to centimeters first, then cancel centimeters squared and get to meters. And meters squared is going to be on the bottom like it should be. Okay, so we know 1 inch is 2.54 centimeters, but we have to square that now this time because that's what the unit tells us to do, right? We're not cubing it, we're squaring it. So because this is squared, we have to square it. So 1 squared is going to stay 1 inch squared. Then 2.54 squared is 6.452 or 6.45 or 6.4516, you pick. All right. And then in the next conversion factor, we have 1 centimeter is 10 to the negative 2 meters, but again, we have to square it. So 1 squared stays 1. 10 to the negative 2 times 2 becomes 1 times 10 to the negative 4 meters squared. All right. So now I'm ready. Calculator, 14.70 divided by 2.205 divided by 6.452 and then divided by 1 EE negative 4. All right, and I get pretty large number. Then I got to think about sig figs. My starting measurement had 4 sig figs. So my final answer is going to have 4 sig figs. So I'm going to take 10,330. The 2 is going to become a 0 just for the placeholder. So 1, 2, 3, 4 sig figs. The 2 goes away, but I need the placeholder of a 0. So this is going to become 10,330 kilograms per meter squared. All right. Okay. So 10,330. That's not a decimal, it's a comma. Again, if you want to do scientific notation, We'll go 1.033 because again, it's very clear. We move the decimal 1, 2, 3, 4 spots to the left, so positive 4 kilogram per meter squared. Okay, so either answer, whichever way you want to report it, works for me. Okay, all right, one more unit conversion. And this one is going to use density as a conversion factor. So when we first talked about density, we were solving mass divided by volume. Now what happens here is density is going to be given to us as a conversion factor. And I want you to think about what we just talked about in the previous example. When you have that slash, that per, right? That's an equivalence line. It's really an equal sign. So question says here, I've got 10.0 kilograms of methanol. And we want to know the volume that would be in gallons. Density is given in grams per milliliter. So starting with the measurement, right, which is the mass, density is going to be the conversion factor because it's got 2 units, it's got an equivalent statement. So that's the conversion factor. So we start with our mass. We're going to convert kilograms to grams. So 1 kilogram is 10 to the third or 1,000 grams. Now the next conversion, we're going to get rid of grams. This is where the density is going to come in, and we're going to go to milliliters. So what I tried to show you here is when you have something with that slash, that per, that is your equal sign. So 0.791 grams is equal to 1 milliliter. Okay, so I rewrote it in a way that makes it look like a conversion factor. The only problem is that conversion factor that only works for methanol, right? Because density is substance specific. So on the bottom with grams, we got 0.791. And then on top with milliliter, just 1 or 1.00. Just don't limit the sig figs with the 1, right? All right. Then to get to gallons, we're going to go milliliters to liters because that's just the prefix. Remember 1 with the prefix, then replace it with the proper exponent. If you don't like that, if you like instead 1 liter is 1,000 milliliters, it works just as well. It's the same thing. Go for it. All right. And then the last one, this is a new conversion factor for us, which is going liters to gallons, but it was on the list of the ones I want you to memorize. And I find that I use it quite a bit. That is 3.785 liters is equal to a gallon. Okay. So on my 1 gallon, it's 3.785 liters. Okay. So on my calculator, 10.0 times 10 to the third, divide by 0.791, and then times 1 times 10 to the negative third, and then divide that by 3.785. And the answer I get here to 3 significant figures is 3.34 gallons. So 10 grams of methanol, or sorry, kilograms would take 3.34 gallons. All right, unit conversions. So if density is given, all right, if density is given, you want to use it as a conversion factor. All right, because density is an equivalent statement of mass and volume. And you always want to start with something that has a single unit if you can, right? In this case, for density, it's going to be a mass or a volume. In this case, we had mass and we were converting to volume. All right, the last thing we have to learn in chapter 1, and we've got 5 minutes, are temperature conversions. You've seen all of this before. The big thing I want you to remember is that whenever you're doing temperature conversions for all 3 formulas, Fahrenheit, Celsius, Kelvin, right? Follow the decimal place of the original temperature, not the number of sig figs, the decimal place. All right. So I do need you to remember these formulas. The Celsius to Kelvin, if you had intro, you probably remember that 273 because we used it a lot for gas laws. For Chem 1, we're going to be more accurate. We're going to say 273.15. If we have Celsius, we're going to multiply by 1.8 and then add 32 to take it to Fahrenheit. If we have Fahrenheit, we'll subtract 32 first, then divide by 1.8. That'll get us to Celsius. There's no direct path from Fahrenheit to Kelvin. You have to go to Celsius first. So first one on there is an example. I'm going to skip it just for the sake of time. We're going to go to the second one. 335 Celsius, convert to Celsius, or sorry, to convert to Kelvin. So formula is when you know your Celsius temperature and you want to convert it to Kelvin, you're going to add 273.15. So pretty easy. 335 added to 273.15. Calculator gives me 608.15. However, what I want to do is look at the temperature that was given to me, and it goes to the ones place. So my final answer can only go to the ones place. So I'm going to round this to 608 Kelvin. All right, so it looks like we followed the sig fig rule, but we really didn't. We followed the decimal place rule. Original temperature went to the ones place, final temperature went to the ones place. The next one is we've got Fahrenheit and we want to go to Kelvin. And for that one, we got to do two different formulas. So step one is we're going to take Fahrenheit and convert it to Celsius. So the way we do that is we're going to take our negative 20.8 Fahrenheit temperature. We're going to subtract 32 first, and then we're going to divide by 1.8. You have to be a little bit careful with this one. On the calculator, I'm going to show you how you can get two different things. If I have negative 20.8 minus 32, enter, divide by 1.8, I get negative 29.3 repeating Celsius. If I'm not careful and I go, okay, I got negative 20.8 minus 32 divided by 1.8, I get a different number. Calculator follows the order of operations. So when I entered it in that way, it divided 32 and 1.8 first and then subtracted it. And we don't want that. So you do have to be a little bit careful here. So make sure when you're typing it in, 20.8 negative minus 32, enter, get your answer. Then divide that by 1.8 and that'll get you your Celsius temperature. Okay. Now follow your decimal place. 1 decimal place, 1 decimal place. So there's my Celsius temperature to the ones place. Now to go to Kelvin, I'm going to add 273.15. Answer's still in there. So I'm just going to go ahead and pick up 273.15. And actually, let me type it in to be careful. All right. So calculator gave me 243.85. Because I'm only going to 1 decimal place, the tenths place, because that's where we started, I'm going to round that to 243.9. So this will be 243.9 on the Kelvin scale. All right. So if you look at that question, it looks like 3 sig figs, but it's not. It's 1 decimal place. That's the focus. And that's why we kept it to 1 decimal place for the answer. Question A that we sort of skipped over, it went went to the ones place. So the answer went to the ones place. Looks like we missed the sig fig rule because we did. We were looking for decimal place, right? So ones place goes to the ones place. Ones place goes to the ones place. The tenths place goes to the tenths place. So that's the rule with temperature. You always follow your decimal place rule. All right. So we are now done with chapter 1. So your homework, and that probably, hold on, let me move this up and do this. Okay, so your homework now is you want to go through your chapter 1 folder. You're going to have practice quizzes. Remember, those are open the entire semester. You can take them as many times as you want. Unlimited time. It's just a good way to help practice the material. The credit quiz is due. So this one you can't leave till the end of the semester. You've got to do it. It's going to be due, today's Tuesday, so it's going to be due Monday, which is the 27th at midnight. All right, technically it's 11:59 p.m. just so it shows up on the right day on the calendar. If I put it in as midnight, it shows up on the wrong day. All right. The other thing I would recommend doing is, again, the TRO homework that I showed you in the Pearson text, the dynamic study guides. All right, the dynamic study guide for chapter 1 in the Pearson text, it's worth 5 bonus points. So you definitely don't want to forget about the bonus points. Bonus points, everybody wants bonus points, right? So definitely don't forget about that. All right, and then there is also in the chapter 1 folder, there is a worksheet there if you want a little more extra practice. All right, so that's everything for chapter 1. Thursday, we're going to come back and do chapter 2. And the question was, with the dynamic study guides, they're going to submit through Pearson. And then after the due date, like they're due the night before the test at midnight, the following day, all I do is sync it to the grade book. And then they'll join the grade book. But everything with the dynamic study guides, the extra credit, it's all kept on the Pearson site. So you just complete those activities on the Pearson site. All right. And if you have any questions this week, getting used to where everything is or finding anything, please let me know. That's what I'm here for. All right. But if you don't have any questions for me, I'll see you back Thursday, either in lab or online at 11:15. I wish you a great rest of your day. All right.
Professor